Hello everyone, and welcome back. Today we're going to be continuing our exploration of real analysis and discuss a very important topic that is associated to the openness and also closeness of sets and intervals, in particular sets and intervals of real numbers. Let's start off with a few definitions of some of the notation that I will be using today, just in case you are not formally familiar with these ideas. So if you see a parenthesis on the left and a parenthesis on the right, and a and b being real numbers, then this is going to be interpreted as the set of all real numbers that are strictly between a and b, not including a nor b. And if you see somebody using brackets, that's commonly interpreted as the set similar to open parentheses AB, except that it includes both A and it also includes B, right? So one could say that bracket AB bracket is just parenthesis AB parenthesis union with the set AB, right? Now, similarly speaking, open parenthesis a comma infinity, so this infinity is the same infinity as mentioned in the extended set of real numbers, and will be interpreted as the set of all real numbers that are strictly bigger than a, and bracket a infinity will be defined to be the set of all real numbers that are greater than or equal to a. So similarly like before, if you have bracket a infinity, this can be viewed as parenthesis a infinity unioned with the number a. And usually people do not put brackets on the infinity boundaries, but if they do, usually they're talking about the extended set of real numbers, if that is the conversation that you're having. Similar definitions can be made for half open, half closed intervals, such as parenthesis a, b bracket, bracket a, b parenthesis, and also the left-hand side of the real line, in particular minus infinity to a and minus infinity to a inclusive, right? So the definitions for those are very similar. So let's also go ahead and introduce another very important definition that we will be using time and time again, and it is the following. So let's assume, let x delta be a metric space. So let x delta be a metric space. If you don't remember what a metric space is, it's just a non-empty set x together with a binary function or binary mapping delta that satisfies four properties. And those properties are like, reflexive, transitive, and the rest of them, right? So we define what is called a neighborhood. So neighborhood of x with radius epsilon, and we're going to be denoting this by n subscript epsilon of x, and it's going to be the set, so a neighborhood is going to be the set defined as follows. So n epsilon of x, so a neighborhood, is defined to be the set of all y in our metric space x, such that the distance between x and y is less than epsilon, where epsilon is an arbitrarily small but positive number. So you can in some sense view that the neighborhood of a point x in the set of real numbers is the set of all points that are arbitrarily close to it, where the distance between the points and its neighborhood, is an arbitrary number called epsilon, i.e. the radius. All right. Now, before we get into a couple of the examples, I just want to mention just something that we proved earlier in the series. So if we take the set x delta with x being the set of real numbers and the distance between x and y to be equal to the absolute value of x minus y, where x and y are obviously reals, then x delta can be proven to be a metric space, right? So if x delta is a metric space prescribed with this particular metric, how can we view this general definition of neighborhoods for this particular metric? So under that particular metric, what do we have? So that means n epsilon x would be equal to the set of all, let's assume, numbers a in the set of real numbers such that the absolute value of x minus a is less than epsilon, by definition, right? So if we use the property of absolute value, then what does that mean? So again, the set of all real numbers such that x minus a is less than epsilon, or actually and x minus a is greater than minus epsilon. So if that is true, then that's going to be the set of all real numbers a such that minus epsilon is less than x minus a is less than positive epsilon. Right? So what I want to do now is I want to subtract all sides of this compound inequality by x, and that's going to give me a new interval. So we're going to have the set of all real numbers such that minus epsilon minus x is less than minus a, and that's going to be less than epsilon minus x. And the next thing that I want to do is multiply both sides by minus 1. So I want to negate that, negate that, negate that. And once I do, that sign is going to reverse in that direction. That sign is going to reverse in that direction. So when I do that, again, I'm going to have the set of all real numbers that satisfy. So negative epsilon minus x would be equal to x minus epsilon. So we're going to have x minus epsilon is less than a is less than x plus epsilon, right? Because those minuses both turn into a plus, and we get this particular interval. But that, by definition, because keep in mind, that's just a real number because x is a real number and epsilon is a positive real number, and x plus epsilon also is a real number, and a is an arbitrary real number. So that means that an epsilon neighborhood of the point x is just going to be the interval x minus epsilon and x plus epsilon. So this is what epsilon neighborhoods look like inside of the metric space x delta, where delta is just that absolute value of distance, right? So a neighborhood is equivalent to this open interval in R delta. And that's pretty interesting and very important to keep in the back of your mind. The next set of definitions that I want to introduce are the main star of the show today, and that's what it means for a set to be open and what it means for a set to be closed. So let's assume that we're working with subsets of the real numbers. So we say that S is an open set, and some people will say that it's open in R, if for each element inside that set there exists an epsilon neighborhood around that point such that that epsilon neighborhood is a subset of that particular set S. Note here that this is not a particular neighborhood, but an arbitrary neighborhood. So it has to be true for all epsilon and also for each x. And we say that a set S is closed if its relative complement is open in R. Now, I want to introduce or mention a very important note that the words open and closed are not antonyms in this context, right? So just because a set is open, that does not necessarily imply that it's not closed. If a set is closed, that does not necessarily imply that it's not open, right? I'll give a couple examples of why I'm mentioning this in just a moment, but keep in mind that open and closed in this context are not necessarily antonyms, right? So just keep that in the back of your mind. All right, let's start proving some things. All right, so let's start with the very important theorem that R is an open set. Right? So how are we going to prove that R, the set of real numbers, is indeed open? So let's assume that we take an arbitrary element, in particular any x, in the set of R, and we're going to let epsilon be an arbitrarily small but positive number. So the question we want to answer is, does n subscript epsilon of x, is this always a subset of R? So if it is true, then that means this is an open set, right? So the question that we really need to follow, because keep in mind, what is an epsilon neighborhood under the typical absolute value metric? Well, that's just going to be, is x minus epsilon and x plus epsilon, is this a subset of R, right? So if that is the case, keep in mind, x minus epsilon and x plus epsilon by definition is equal to the set of all real numbers such that x is strictly between x minus epsilon and x plus epsilon. Well, actually, I should change the notation or the element that I'm using to point focus on, so it should be like a, right? So it's a set of all numbers a such that that inequality is matching, right? And since it's a set of real numbers, that means it's a subset of R, right? So it's a subset of R, always. So that's great. So, and since also, you could also say, just to add a little bit more context, if a is a real number and epsilon is a real number, x minus epsilon, x plus epsilon, they're also real numbers as well, right? So that's definitely a subset. So that means what? So that means R is an open set, right? So that's pretty neat, I guess, and very important to keep in mind. And let's go to its complete opposite character, the empty set. The empty set is also an open set. Okay, so how are you going to prove that the empty set is an open set too? So take any x in the empty set. Now think about that for a moment. Technically, we can't, right? So that means, what do we have? So the definition of open doesn't fail, right? Because we can't prove that a epsilon neighborhood of this chosen question mark x isn't a subset of the empty set. And we know that the subset is a subset of itself, technically speaking, right? So since the definition of open does not fail, that means this statement that the empty set is open is vacuously true. And if that is vacuously true, then we have that the empty set is an open set. Right? So it's a very subtly awkward statement, but it is technically true by definition and logic. Right? So that's cool. But the next theorem actually is a little bit more interesting. R is closed. Right? Now keep in mind, we've already proven that R is open, and now I'm claiming that R is closed too. Right? Now, if you view closed and open as antonyms, then technically this would be impossible and lead to a contradiction to that previous statement, right? But as I mentioned, they're not necessarily antonyms, right? So let's see if we can go ahead and prove that R is closed. So how do we prove that the set is closed? Well, that means its relative complement, which is going to be R take away R. So if we take R and you take away everything in R, practically we're left with the empty set. We know that the relative complement with respect to R, we know that this is open, right? So since RC is open, that means R is closed. Okay? And that gives us that. So R is both open and closed. The next theorem, what about the empty set? The empty set also is closed. So how are we going to go about proving that? So if we take the relative complement of the empty set, which by definition is R take away the empty set, so if we take R and we take away nothing, what are we left with? Well, we're just left with R. We already know that R is open and also closed. But since the relative complement of that is open, that means that the empty set is closed as well. Right? So the empty set also is a set that is both open and closed. Okay? So let's go ahead and introduce a definition, and let's sort of add on to the previous set of definitions. So we had the definition of open, the definition of closed. Let's add the next definition of a clopen set. So if S is both open and closed, we call S a clopen, both closed and open set. Okay? So that means, from our previous discussion, that R and the empty set are clopen sets. So that's pretty interesting. Now, question, are they the only ones? So that's where the next theorem enters the conversation. So theorem, let's call it 5, right? So R and the empty set are the only clopen subsets of the set of real numbers. I'm not going to actually prove this for you because actually the proof is not too difficult, so I'll just leave it for you. Right? So think about, what if there was another set inside of here that was neither R nor the empty set? What kind of properties would it have? Right? So give that a go. You may pause this video and we can recontinue when you get back. Okay? So the next theorem that I want to look into is actually very important as well. And it says the following. The union of a set of open sets in R is also open in R. Right? So a set of open sets is open under unions. And this union can be a finite union, a countably infinite union, and also an uncountable union as well. All right? So let's see if we can go ahead and prove that the union of open sets of real numbers is also open. So how are we going to go about doing that? So let's suppose that the set of open sets is of size, let's call it omega. And let's assume that this omega is either finite, implying that it's in the set of natural numbers, or countably infinite. Right? So if it is either finite or countably infinite, that means you can find a bijection with respect to the set of natural numbers. Right? So if that is the case, what we're going to do is we're going to let x be an element of the union from k is equal to 1 to omega of these sets sk, right? So in some sense, we're enumerating this set of open sets, okay? And here, where this sk set is our set of open sets, right? So S1, S2, S3, S4, all the way down to S omega are all open. So if it is in the union of these sets, then where does x belong exactly? So if it's in the union, that means x is an element of Sn for at least one n within the set 1, 2, 3, down to omega, which is practically our indexing set where we're indexing this particular union. Agreed? So if that is true, what else can we say? So since this particular set, at least one of these sets, for which x belongs, since this Sn is open, that means there exists an epsilon that is arbitrarily small but positive, such that a neighborhood of radius epsilon around x is a subset of Sn. That's the definition of an open set, and Sn is indeed open because it belongs to our set of open sets. Right? So if that is the case, then since n epsilon x is a subset of Sn, and we also know that Sn is a subset of the union from k is equal to omega of xk, because it's one of those sets, then that means that n epsilon of x is a subset of the union from k is equal to omega of xk, right? So that means we have an arbitrary neighborhood within our union of sets. And if that is the case, that means the set union from k is equal to infinity of xk is open. And if you want to change this proof for an uncountable set, all you have to do is just change your indexing set from, instead of, say, 1 to infinity, which is practically an enumeration of the naturals, you just need to do an indexing set for, say, the real numbers or any other set that is not bijected to the set of natural numbers, right? But as long as you can define your indexing set, the proof is practically the same. So we've stated and proven that a union of open sets is open, and that union can be a finite union, a countably infinite union, or even an uncountable union of open sets, and we still get an open set in the end. The next theorem states the following, that a finite intersection of a set of open sets will also be open, but very important keyword here, finite. So you may even start to think about, well, what's the problem with countably infinite and uncountable intersections of open sets, right? Why isn't it still an open set, right? And there's several counterexamples that you could build for that, but I'll let you think about that on your own, right? But this theorem says it is at least true for a finite intersection. So let's see if we can go ahead and prove this. So let's suppose that the set of open sets is of size n in the set of natural numbers. And we can assume this because we're assuming that we have a finite intersection of a set of open sets. And what we're going to do is we're actually going to explicitly define the set. Let's actually give this set a name. Let's call it omega. So this is going to be equal to the intersection of all of our sets. So let's index it with respect to a subset of the naturals from k is equal to 1 to n of xk. And here our sk is the same exact sk as before. This is our finite collection of open sets, right? So our question to answer is omega open, right? So one of the assumptions that we have here, so assumption is that sk is open. And that's true for all k is equal to 1, 2, 3, all the way up to some finite number n, okay? So if this is open, then what must be true? So the first thing we're going to do is we're going to choose an arbitrary element inside of omega, which in short term is a fancy way of writing x belongs to the intersection from k is equal to n of xk, right? So if it's in the intersection of all of them, that means x belongs to xk, and this is true for all, not at least one, but for all k in the set of natural numbers, right? So, well, not in the set of natural numbers, but in that subset, right? 1, 2, all the way up to n, right? So if that is true, so it's in each of those open sets, right? So in all of the open sets, in all of them, right? So if that is true, so we're going to do n neighborhoods at the same exact time. So let's see if you can follow. So that means there exist a bunch of epsilons, and we're just going to create a sequence of them. Let's call it epsilon k, where k ranges from 1 to m, such that these neighborhoods, epsilon k surrounded by x, are subsets of those individual open sets. And here, each of these epsilons are positive, and that's true for all k from 1 to m. Okay, so these are n neighborhoods because we have n open sets. Okay, so what is true about these epsilons, right? So the first thing that is true is that these epsilons are positive. So since epsilon k are always positive, and that's true for all k, and also this set epsilon k from k is equal to 1 to m, it is a subset of the set of real numbers, and it's also bounded below by 0, because all of them are greater than 0. That means, 0 is a lower bound for that subset of real numbers. Then by Zorn's lemma, and what does Zorn's lemma say? So since we have a subset of the real numbers that is bounded below, that means this set, epsilon k from k is equal to 1 to n, has a minimal element, right? So if it has a minimal element and it's guaranteed to exist by Zorn's lemma, what we're going to do is we're going to let epsilon be equal to that minimal element. So it's going to be the minimum of epsilon 1, epsilon 2, all the way down to epsilon n. Okay? So if that is the case, So let's sort of zoom out for a bit and sort of see what we have here. So we have x, we have some neighborhoods that are sort of bigger and bigger and bigger. So epsilon, its neighborhood, is going to be the smallest one of them all. Okay, so if that is the case, what we have here is that n epsilon of x, where epsilon is the minimum of those radii, that's going to be a subset of n epsilon k of x, and we know that n epsilon k of x is a subset of sk. If that is the case, what we have here is n epsilon x is a subset of the intersection from k is equal to n of your xk, and since this n epsilon x is an arbitrary open neighborhood of that intersection, that means we have that the intersection from k is equal to n of xk, also known as omega, is an open set. Right? That's a very nice and quick proof for that. And again, this only says that a finite intersection of open sets is open, and I very highly encourage you to see if you can find a counterexample for infinite intersections of open sets not being open. The next theorem that I want to explore is sometimes called the nested interval theorem, and it says the following. Suppose that you have a set of intervals, which are abbreviated by ik, and they're closed intervals, right? So it's a bunch of closed and also bounded intervals, right? In some sense, if it's a closed interval and it's a subset of R and it's practically one interval, not a bunch of them, one can actually show that if it's closed, it's also bounded both above and below, if you're working with finite numbers ak and bk. Right? So let's assume that we have a bunch of closed and bounded intervals. And what do I mean by a bunch? You can either take a finite number of closed and bounded intervals, or you can take a countably infinite number of closed and bounded intervals, right? So this n star could be infinity, where k is equal to 1 to infinity is just an enumeration of the set of natural numbers, for example. Right? And these intervals must satisfy the property that I1 is a superset of I2, and I2 is a superset of I3, all the way down to IN, a superset of the next one in sequence. So that means I1 is sometimes reviewed as a covering of I2, and I2 is a covering of I3, and IN minus 1, or IN minus 1, or plus 1 actually, is a covering of IN. Right? So these intervals get smaller and smaller and smaller. Now, if this sequence, is what some people call it, of closed and bounded intervals does have this little nested property, then this theorem says that there exists a real number that belongs to every single one of them. Right? So let's sort of draw a picture to sort of see what we have here. So if we have I1, right? So this is our set of real numbers, and I1 is going to have A1 and B1 in it, so that's our I1. And then I2 is a subinterval of that, so there's A2 and B2. And then we have I3, which is going to be A3 and B3. And then we sort of continue all the way downwards, and we have, for example, IN, which is AN and Bn, and this either can stop at In or it can continue onwards, right? But in some sense what you have is what we call a telescoping interval sequence, right? So this theorem says that there exist, now notice it doesn't say unique, right? It doesn't say unique, but in some sense if this always converges or always gets smaller and smaller and smaller, that is, we remove these little equality signs and then we have a proper infinite sequence, then in some sense it has to collapse to a single point in that sort of interval of size 0, one could say. Right? So let's see if we can prove this very fascinating and actually very important theorem. Right? So let's see if we can provide a fun little proof for this. So the first thing, and from this picture you get a lot of interesting and obvious things. So the first thing is that ik, so interval ik, is a subset of I1 because I1 is the biggest set of them all, and this is obviously true for all I'm going to say k in the set of natural numbers. If you have a finite collection, then it's just a subset of the naturals, but this is a little bit more general. All right, so that's going to be true for all k in the set of natural numbers. And if that is true, then what you have is that ak is going to be less than or equal to b1, and that's going to be also true for all k in the set of natural numbers. So what am I exactly saying with this particular statement? So ak is the lower bounds of those intervals. So we have a1, a2, a3, down to an. They're always less than or equal to the greatest upper bound, which is associated to I1. Right? So if that is true, then what do we have? So that means the set, which I'm going to define to be S, of the lower bounds of this sequence, here k is going to belong to the set of natural numbers. Obviously, this is not an empty set because it has to have at least I1 in that sequence. This is bounded above by B1. Okay? So if that is the case, what exactly do we have? So we have a set and an interval. So it's the set of interval lower bounds, right? And in some sense, since they're closed, they're also infimums of those intervals as well, right? And keep in mind, we're in subsets of the set of reals. So what we can do is we can define x to be the supremum of S, okay? Because we have a subset of the real numbers that is bounded, in particular it's bounded above, therefore there exists a supremum for the set that also belongs to the set of real numbers, right? And also, not only does it exist, it's also unique, which we've proved in the past, right? So our goal, so let's sort of diverge for a moment. So our question, does x, which is equal to the supremum of this set, does this belong to this interval for all k in the set of natural numbers? All right, so does the supremum of all of the lower bounds belong to all of the intervals? And you might need to take a step back and let's actually look at this picture, right? So is A1 the supremum of that sequence? Well, that would be no, because A2 would be bigger than A1, right? And what about A3? Well, A3 would be greater than or equal to A2, so A3 would then be the upper bound. And this is going to go to AN. Is AN the supremum of that set? Well, it depends. Does the sequence stop at IN? If the answer is no, then there has to be another number up here that either is a lower bound for one of these intervals, or there has to be another number that does not belong to this interval that's always greater than or equal to that sequence AM. Right? And obviously, if that is the case, can we get above this particular number x? For example, could x be right here? The answer would be no, because these a's are never going to surpass their upper bound, right? For example, an cannot be bigger than bn, and a3 cannot be bigger than b3, so x cannot be above any of those b's, right? So in some sense, these lower bounds are converging upwards to that, what we call an accumulation point, I guess you could call it. And you could also argue that the b's are also converging downwards to this number x, because keep in mind, these intervals are relatively symmetric about their median, right? So is this supremum of lower bounds actually this point that always exists? Okay, so let's sort of walk through this and see if we can build a nice little argument. So the first thing that I want to sort of observe is if n is less than or equal to k, what can you tell me about the intervals ik and in? Which is bigger? You might want to take a moment, pause the video, and sort of think about this. So if n is less than or equal to k, which one is a subset of who? You should be able to conclude that ik is a subset of in. And if that is the case, what can you conclude from that in terms of AK, BK, AN, and BM? You should be able to conclude that AK is less than or equal to BK is less than or equal to BM, right? And we get that BK is less than or equal to BN since they're subsets of each other, and Bn is the upper bound of In, and In covers Ik. Right? So the second thing I want to notice is the other direction. So if k is less than m, so that covers both of these scenarios, then what do we have about In and Ik? Well, if that is the case, then that means In is a subset of Ik, or Ik is a covering of In. And if that is true, what do we have? Again, we have that AK is less than or equal to AN, and that's going to be less than or equal to BN, right? And practically what we have here is that AK is less than or equal to AN because IK is a covering of IN, so AK is slightly, beyond that other set, okay? Right, and keep in mind, these A's are on the left and the B's are on the right, okay? So from these two, what do we have? So we have that AK is less than or equal to Bn, and we also have that AK is less than or equal to Bn in this particular case too. So we have that AK is less than or equal to Bn for all k in the set of natural numbers or the subset that you're working in. So if that is the case, that means Bn is an upper bound for S. And that's a lot better than what we started off before, because originally we had just B1 was an upper bound for S, but now we have that Bn is an upper bound for S as well. Right? So what can we get from that? So that means this point, the supremum, must be less than or equal to Bn, and that must be true for all n in the set of natural numbers. In particular, An must be less than or equal to x and less than or equal to Bn, and that again is true for all real numbers n, right? So natural numbers n, right? So we have this particular thing. But what is An and Bn? Well, that's just In, right? And here n is an arbitrary natural number. And x is directly in between it. So that means x, which keep in mind is a real number, belongs to Im. And that's obviously true for all n in the set of natural numbers, which was what we sought out to prove for the nested interval theorem. So if you have this nested sequence of intervals that are sort of nested within each other, then you're always going to have a point that belongs to every single one of them. So throughout this video, we've been talking a lot about openness and closedness of sets, and we've actually discussed quite a few theorems about open sets and closed sets, in particular about unions, intersections, and also ones that are nested within each other in some sense that form a sequence. Right? Now what I want to do is I want to revisit a topic that we talked about earlier, in particular the countability of sets. Up to this point, we've actually already proven that n, z, and q are all countable sets. In particular, they all have bijections to the natural numbers, so at least from that perspective, you can say they have the same exact infinite cardinality, in particular LF1 or LF null. So now what I want to do is I actually want to answer the question before, does R also have a cardinality that is equal to n, z, and q, implying that R is also a countable set as well. Right? To sort of start off that discussion, I want to introduce this next theorem, which I'm going to call theorem 9, and we're just going to be focusing on a subset of the reals, in particular the interval 0, 1. Right? So this theorem says the following: the closed interval, 0, 1 is not countable. All right? And keep in mind, 0, 1 is a subset of R, so if 0, 1 is not countable, that means R is not countable either, right? So let's see if we can prove this wonderful, beautiful theorem. Right? So what we're going to do is we're just going to assume that S, I'm just going to define S to be equal to 0, 1. Let's assume that it is countable. Right, so if it is countable, that means there must exist an F that is a bijection, and it has to be a bijection from the set of natural numbers to this set S. Right, so that means there exists this set S, and let's assume that we have listed the elements of S, so x1, x2, x3, all the way down to say xn, and so on. Let's assume that this is the enumeration of S, right? So here, 1 is going to x1, 2 is going to x2, 3 is going to x3, n is going to xn, and so on. Right? So this is the enumeration of 0, 1. So this set here, these are all of the real numbers from 0 to 1 listed here in some particular order for which I'm enumerated from 1 to n and so on. Okay, and you might be able to think, okay, well, is that really possible? Technically no, because we're trying to prove by contradiction, right? All right, but let's see if we can get our contradiction. So by the axiom of choice, what I want to do is I want to choose a set S1 that's going to be a subset of S such that the first element, x1 does not belong to S1. And then I'm going to choose set S2 that's a subset of S1 such that x2 does not belong to S2. And then I'm going to choose S3 that's a subset of S2 such that x3 is not an element of S3. And then I'm going to do this as many times as I can. So what exactly do I have? So practically what I'm doing is I'm eliminating these terms one by one in the same exact order for which I've enumerated them. So my biggest set in this sequence obviously is going to be equal to S1, and then we have S2 underneath that, and then we have S3 underneath that, and this is going to continue onwards all the way down to Sn, and this is obviously going to continue downwards since we're working with the entire set of natural numbers, and that's the enumeration, right? So what have I built here? Well, I've built a nested sequence of sets, right? So the next thing I need to justify is, is this closed? Is this bounded, right? So let's target the first statement that's actually a little bit more easier to deal with. Bounded. So it's bounded below by 0. 0 is actually the infimum of closed interval 0, 1. And it's bounded above by 1, which is actually the supremum of 0, 1. So it's definitely bounded. So what about closed? Closed, right? So in particular, we have 0, 1, which is a closed interval. So if we were in some sense defining this set to be closed, then life is good. But its complement, right? So if we look at the complement of this, which is actually minus infinity to 0, and then union 1 to infinity, it's actually a little bit more easier to prove, at least by definition, that that is an open set and that is an open set, implying that the interval 0, 1 is actually closed, right? Because if you build a neighborhood around 0, you're going to have some negative numbers in there. If you build a neighborhood around 1, you're going to have some numbers bigger than 1 in that neighborhood too, right? So that in some sense is going to be implying that that's a closed interval, right? So if we have that, we have a bounded, closed, nested sequence of real numbers, then what does that mean by the nested interval theorem? So that means there exists, not necessarily unique, but there exists an x within S such that x belongs to Sk for all natural numbers k. Right? Now keep in mind, if x belongs to Sk, that means, keep in mind, Xk is not belonging to Sk by construction. So if x belongs to Sk and Xk is not in Sk, that means what about x? Well, that means that x does not equal to Xk, right? Since they were removed from our sets, right? So if that is the case, that means our bijection, f is missing at least one element from our set, in particular x. Because if x does not equal to xk, and keep in mind, x belongs to sk for all k in the set of natural numbers, that means x is not equal to xk for all k in the natural numbers. And since we've created a bijection from n to s, that means x has to belong to that bijection. But we're missing something, right? So that would be implying that, this set is not on 2, right? So that means that this interval, 0, 1, is uncountable, right? So you could either view that as a sad thing or a happy thing. It depends on your perspective, right? So 0, 1 is not uncountable. And what do we get as a result of that? And let's call this theorem 10. Since 0, 1 is a subset of R, we have as a direct result or a corollary that R is also uncountable. And you could get several lemmas from that. In particular, there does not exist a bijection from N to R. That would be the first corollary that you could get. Right? But that's some of the little applications and theorems associated to open sets and closed sets and open intervals and closed intervals of real numbers. Hope you enjoyed this video, and I'll see you in the next one. Take care.